This is Physics 2120, Lecture 15, and today we're going to continue talking about sources of the magnetic field. In particular, we're going to deal with Ampere's law and magnetic flux. Now, Ampere's law gives us a way of calculating the magnetic field in symmetric situations. It's going to be similar to a process that we did with Gauss's law, where Gauss's law allowed us to calculate the electric field when we had some symmetries. So in Ampere's law, the product of B dot ds is evaluated for small length segments ds on a circular path defined by the compass needle for long straight wires. Ampere's law states that the integral of B dot ds around any closed path is equal to mu naught I, where I is the total steady current passing through any surface bounded by the closed path. Or the integral of B dot ds, and the integral of the circle, remember, it means over a closed path, is equal to mu naught I enclosed. Ampere's law describes the creation of magnetic fields by all continuous current configurations. And again, this is most useful for this course if the current configuration has a high degree of symmetry. I put my thumb of my right hand in the direction of the current through the Amperian loop, and your fingers curl in the direction you should integrate around the loop. So let's go back to the problem we did last time, a field from a long straight wire, and we're going to do this during Ampere's law. And I want to calculate the magnetic field at distance r from the center of a wire carrying a steady current I. This time we're going to look at both the magnetic field in the wire and outside the wire. We're going to assume the current is uniformly distributed everywhere in the wire. So we start with integral B dot ds equals mu naught I again. In this case, if we're on the outside, if we're looking at the outside, the current enclosed is all of it. Now let's look at the integral B dot ds. Well, everywhere along this path we know from symmetry the magnetic field has to be the same. And B is going to point in the direction that I'm integrating, this little ds. So the dot product gives me 1. The b comes out, and I integrate ds. Well, integrate ds is just the length of this path, which is the circumference, which is 2 pi r. So now I equate those things, solve for b, and I get b is equal to mu naught I over 2 pi r. We can see this is a lot easier than using the Biot-Savart law that we did last time. Also gives us the exact same answer. But the thing that Ampere's law does is it also allows us to figure out what the magnetic field is inside the loop. So in this case we start with the same thing. The integral B dot ds is mu naught I enclosed. But I enclosed is, well, I know that the total current divided by pi r squared is the same as the enclosed current divided by pi times little r squared, since it's uniformly distributed. So I enclosed is I times r squared over big R squared. Now we just plug that in to the integral that we have before, because it's the same integral. Integral B dot ds is given to give me b times 2 pi r, mu naught I r squared over r squared, and we get inside the magnetic field mu naught I over 2 pi r squared times r. So the magnetic field is going to increase linearly on the inside, and it's going to decrease like 1 over r on the outside. If I were to graph this, we'd see exactly that. B is proportional to the r on the inside of the long straight wire, and then it goes down as 1 over r squared. Both equations are equal at little r equals big R. We also figure out the magnetic field from a toroid. Let's find the field at a point at a distance r from the center of the toroid. And this toroid, remember, is like a donut shaped, has n turns of wire. Now, I've got a couple of Amperian loops that I can use that are shown here. I've got this one here, and I've got this one here. And the question is, which one shows the symmetry? Well, in this case, this Amperian loop here there's no reason to think that the magnetic field on the inside and the outside are going to be the same, and so there's no symmetry. However, everywhere inside this toroid, a distance r away from the center, has to have the same magnetic field due to the symmetry. So we're going to use this ring. So, when r is less than b, when it's in here, mu naught I enclosed is equal to 0. Because there's no current, there's no wire piercing a loop drawn in here. Similarly, out here, if I draw my Amperian loop, there is no current going through. I'll have, if I draw the surface here, I'll have some current coming out, but it always goes back in. So the net current through my loop is 0. However, when I'm in between B and C, and I draw my Amperian loop here, it goes down inside here, and it comes back on the outside and down. So every time I go down inside, I have more current going through my Amperian loop. The total enclosed current, then, is the number of turns times the current in each turn. So then, since I know B is symmetric, the integral B dot ds is still B times 2 pi r. That's equal to mu naught in I, or the magnetic field inside the toroid is mu naught in I over 2 pi r. The magnetic field outside the toroid is 0. And next, let's look at the magnetic field from an infinite sheet current. So let's assume I have an infinitely large sheet, and it carries a current density, J. The current is going to be in the y direction, which in this case in the picture is out of the paper. So J sub s represents the current per unit length along the z direction in this figure. We're going to use a rectangular Amperian path in this case. Now, the W sides don't contribute to the magnetic field. If I do my right-hand rule, stick my thumb coming out of the page here, I know that from each little segment, the magnetic field is going to go around. And if I add up all of these, all the components that are going in and out are going to cancel out. If I look at say this one, and would be coming around here, and this one be coming around here, the in and outs cancel, and all I end up with magnetic field going up in this direction and down on this side. So, as I'm integrating around my Amperian loop, B dot ds along the top and bottom is 0 because B and ds are perpendicular to each other. On the sides, I get B out here, and ds is going to be L, and as I'm coming up this side, I'm going to get B times L, and so integral B dot ds becomes 2BL. Now, I have to figure out the current enclosed. The current enclosed is going to be the current density, the current per unit length, times the length enclosed by my Amperian surface, so JL. So I put those two things together, and I get B is equal to mu naught J over 2. In other words, the magnetic field from an infinite sheet of current is constant, and it is parallel to the surface of the current. We can also look at a solenoid. A solenoid is a long wire that's wound in the form of a helix. And a reasonably uniform magnetic field can be produced in the space surrounded by the turns of the wire, or the interior of the solenoid. Around the wires it gets a little bumpy, but in the center it's fairly uniform. And this uniformity increases the tighter I get my coils. So the field lines on the interior are approximately parallel to each other, they're uniformly distributed, and they're close together, and that indicates it's a strong field. So we have a strong, uniform field inside a solenoid. And the field distribution of a tightly wound solenoid is very similar to that of a bar magnet. As the length of the solenoid increases, the interior field becomes more and more uniform, and the exterior field becomes weaker and weaker. An ideal solenoid is approached when the turns are closely spaced and the length is much greater than the radius. So when the length of the solenoid is much bigger than the radius of the solenoid. We can apply Ampere's law to find the interior magnetic field of the solenoid. In this case, we want to use this rectangular Amperian loop. We don't want to draw an Amperian loop around the solenoid. We want, since it's uniform, we want it to go in like this. So, as I do mu naught I is equal to the integral b dot ds. Well, if we integrate b dot ds, b and ds are perpendicular along these paths, so they don't add up. We said the magnetic field is 0 on the outside, so 3 doesn't add to anything. All we get is b times L. So, apply that to Ampere's law, integral b dot ds becomes BL. The total current through the rectangular path equals the current through each turn multiplied by the number of turns. Typically then, we divide by L and we get its mu naught N over Li, or little n(I), where little n is the turns per unit length of the solenoid. Now this equation is only valid near the center of very long solenoids, but we can use it, solenoids, to create very uniform magnetic fields to perhaps do experiments or other applications when we need a uniform magnetic field. Now, as we did with electric fields, we talked about electric flux, and remember, flux is the number of lines through a surface. So the magnetic flux associated with magnetic fields is defined in a similar way. We consider an area element, dA, on an arbitrarily shaped surface. The magnetic field in this element is B. dA is a vector that's perpendicular to the surface and has a magnitude equal to the area of the surface. And the magnetic flux then is defined as the integral of B dot dA. The unit of magnetic flux is a Weber, or a Tesla meter squared. Notice a typo. This should be a capital V. Now, a special case of flux is when a plane of area A makes an angle theta with dA. The magnetic flux is equal to BA cosine theta. In this case, the field is parallel to the plane and the flux through it is 0. Here the magnetic flux is again BA cosine theta, but now I have the field perpendicular to the plane, and so the flux through this plane is just B times A. This is going to be the maximum value of the flux. Now we can also apply Gauss's law to magnetism. Now, magnetism, remember, the magnetic field lines have no beginning or ending point. So the number of lines entering any closed surface has got to equal the number of lines leaving a closed surface. So Gauss's law in magnetism says the integral of B dot dA is equal to 0, because there's no magnetic charge to be enclosed in this surface, like we had with electric fields, where the integral of E dot dA was Q enclosed over epsilon naught. So Gauss's law in magnetism, integral B dot dA equals 0, says magnetic field lines do not begin or end at any point. So let's review what we talked about today. We talked about Ampere's law and how we can use Ampere's law to figure out the magnetic field in symmetric situations. We introduced the idea of magnetic flux, which was similar to electric flux, and we're going to use it in similar ways. And we quickly stated Gauss's law in magnetism, which is the integral of B dot dA is equal to 0.